Hey guys, so what's the big idea in calculus? Well, the big idea with derivatives, at least, is rate of change. So today we're going to talk about rate of change and then move into the definition of derivative. So first, here's a whole bunch of vocabulary, so if you need to pause me, I understand. Slope, like we've been learning about since Algebra 1, is the steepness of a line, and that's also just rate of change. A secant line is a line that passes through 2 points of a curve. So you might remember secant lines from when you were in geometry. They were lines that passed through 2 points of a circle. If you look back in my classroom where I have that hula hoop, I have that line that passes through 2 points through a circle. That's a secant line. I bet you remember that. You might remember a tangent line from geometry as well. That's a line that only intersects a circle at 1 point. So a tangent line is a line that intersects a curve at exactly 1 point. Ooh, forgot the word point on there. There we go. A gradient is a fancy word for slope, and people tend to use the word gradient in calculus more than they use the word slope. So gradient is the slope or the rate of change of a function. It's also the same as the derivative. So if you're asked to find the gradient, you should be finding the derivative. And a derivative is the gradient or the rate of change of a function. So we're going to be learning about how do we find a derivative, what is it, all that sort of stuff. So first thing, when I think about rate of change, I think about miles per hour or liters per second, something like that, something per something else. So remember, slope is rate of change. So if you have some sort of linear situation, like this guy right here, where we have miles and hours, maybe in 3 hours you end up going 180 miles. Well, if you're going constantly the entire time, it's really easy to find that rate of change. We just find the slope between those 2 points. So if you remember from Algebra 1, slope is y2 minus y1 over x2 minus x1, or change in y over change in x. Not sure if you know this, that little triangle there, that is a delta. And delta means change in. Not sure if you've seen that happen in physics or something like that before. And that's also going to be good old rise over run. So if we want to find the rate of change between those 2 points, we would take our y terms and subtract them, 180 minus 0, divided by my x terms, subtracted 3 minus 0. So remember, it doesn't matter which one is your x1 and your y1 and which one is your x2 and your y2, as long as you keep those 2 points together. So when I simplify this, I end up with 180 miles over 3 hours. And then when I simplify that, I end up with 60 miles per hour. And sometimes this is written miles with hours with a little -1 as the exponent. Sorry, the dog is trying to get some blanket. Here you go, puppy. Oh, it's a little chilly. There you go. There's the blanket. Okay. Sorry. So what happens if we are not given a linear function? How are we supposed to find the rate of change? Well, one way to do that is to find the rate of change over an interval. So maybe we have a function that looks like this. And maybe this is feet. And maybe this is seconds. maybe our function looks like this. Well, maybe we're trying to get our very best guess for what the instantaneous rate of change is at 2.5 seconds. So maybe we have information for this point right here, which is at 250. And maybe we have information for this point right here, which is at 325. So what we can do is we can find the slope of the line that passes between those 2 points. It's a really good guess for the slope of the line right at 2.5. Now, since this passes through 2 points in the curve, remember, that is my secant line. So we can find the slope of this line. We can take 50 minus 25 over 2 minus 3. And we'll end up with 25 feet over -1 second. And we'll end up with -25 feet per second. Or sometimes that's written -25 feet. And then seconds with a little negative first on it. Remember, we saw that back when we had our vectors unit. So, sometimes we really would love to find instantaneous velocity or instantaneous rate of change. So, what can we do to find at that very, very moment? So, what we can do, if we want to do this, we want to start trying to make those 2 points as close as possible as we can, right? So in that last one, if we were trying to find the slope of the line at 2.5, finding the slope between 2 and 3 gives us a pretty good guess. So here's what I would love for you to do. I would love for you to pause me, go to Desmos, click on those 3 lines up in the upper left-hand corner, and then click on Calculus Secant Line. And then go ahead and play around with the H value right there. And see what you notice about those functions. Alright, so when you come back, let's take a look when H is really, really small. So if we think about having H be as close to 0 as we can, if we have H be 0.0 or 0.1, our slope right here is 0.12 or 1.26. And then on the other side of 0 at -0.1, we are at 0.28. So we know we're going to be right smack in that 1.27 area for our slope there, right? But what exactly is it going to be? Well, if we want H to be 0, check that out. That's undefined. So this is where we're going to have to start using that concept of limits that we've been using. Let's give our best guess of what the slope should be when H is equal to 0. So I don't know if you've noticed, but we have this little formula for slope in there, in that 4th box, where we have our y values subtracted, divided by the distance between those, the x distance between those y values. So, let's take a look at that. That formula is something that we are going to be using quite a bit. It's really just slope, right? The y values, the f of x's, subtracted by the distance between those, or divided by the distance between those two the x distance between those 2 points. So what this really is that is the slope, it is the way to find the slope of the tangent line, or the instantaneous rate of change, or the gradient of the tangent line, or it's the definition of derivative, or it's the difference quotient. It's this, essentially the slope of a line, f of x plus h minus f of x divided by h, but trying to get h as small as we possibly can. So we'll have the limit as h approaches 0. So this is a big deal. This is the definition of what a derivative is. So if you are ever asked to find the derivative of a function by definition of derivative, this is what you are going to do. So let's go ahead and look at some problems finding the derivative, or finding one of these different things. So the questions can be asked in a lot of different ways, but they're all asking the exact same thing. So the first example I have for you is I want you to find the gradient of the tangent line of this function. I'm just going to put tan line. So remember, gradient is just a fancy word for slope. But we should try to use gradient as much as we can. And please remind me to use the word gradient. So we're starting off nice and easy. Just get the idea of this. So we're going to say that, I'm sorry, not y. Let's say that we have f of x equals 2x plus 3. Alright, so we're going to pop it into this formula where we have the limit as h approaches 0 of, now first of all we have f of x plus h. Remember, x plus h needs to go inside of my function. So I'm going to have 2, and then instead of just having x there, I'm going to have x plus h plus 3. And then I'm supposed to subtract all of f of x. So my life advice is to put parentheses around all of f of x. So that way you remember to distribute that negative on through. And remember, all of that is going to go over h. So now we're just going to go ahead and simplify this a little bit. The limit as h approaches 0 of 2x plus 2h plus 3 when I distribute that 2 on out. And then I'll distribute that negative on out. So that way I have minus 2x minus 3, and all of that goes over h. So here's what's going to happen in this next step. I'll have the limit as h approaches 0. Now if you notice, my 2x cancels out, and so does my 3. All I'm left with is just 2h, and that'll go over h. Now in every single problem, all terms without an h should cancel out at that point. If all your h terms didn't cancel out, something has gone terribly, terribly wrong. Alright, so let's continue on through here. My h's will cancel out. They'll divide away to 1. So we'll have the limit as h approaches 0 of 2. And like you saw in your limit stuff from yesterday, if I'm taking the limit as h approaches 0 of 2, Well, my answer is just going to be 2. So that is the gradient of the tangent line. So now we knew that was going to happen because we know what the slope of a line is and all of that sort of stuff, and that's wonderful. But I just wanted to get you one that was kind of easy to deal with first off, so that way when we have some ickier ones, you'll know what to do with them. So let's move on to one of those slightly ickier ones. All right, so this time we want to find the difference quotient. Now, finding the difference quotient is the exact same question that they asked me last time. So I'm going to go about it in the exact same way. So this time I have g of x equals x squared plus x plus 3. So something a little bit more complicated. So we'll pop it into that formula, or difference. It's usually called the difference quotient formula. So we'll have the limit as h approaches 0 of, and then wherever I see an x, because remember I need f of x plus h. So I need x plus h wherever I see an x in my function. So I'll have x plus h squared plus x plus h plus 3 minus, and then I'll subtract that entire function, x squared minus x plus 3. And that will all go over h. So then we'll go through and we'll start simplifying. So I'll have the limit as h approaches 0 of, and this is going to get a little bit long, but that's okay. Now when I go through and I actually multiply out x plus h times x plus h, when I distribute on through, I end up with x squared plus xh plus xh plus h squared. So when I combine my like terms right there, I'm going to end up with x squared plus 2xh plus h squared when I multiply out that binomial. And then I have plus x plus h plus 3. And then I'll go ahead and distribute on out that negative into my f of x. So now I have minus x squared. Oops, I made this a minus already. Oops. So now I have minus x minus 3. And then all of that is going to go over h. So now, like I mentioned last time, at this point, all non-h's should cancel out. So if I have terms without h in it, they should cancel out. But if they don't, something's gone wrong. So don't just assume that they did. Actually go through and check your work. So the limit as h approaches 0. Let's see. Good, my x squared cancels out, my x cancels out, and my 3 cancels out. Cool. So now I have 2xh plus h squared, that's left over, and then I have another plus h, and then everything else had added to 0. So all of that went over h. So if you notice in my numerator, each one of those has an h. So we have the limit as h approaches 0 of, and since all of those have an h in my numerator, I can go ahead and factor one out. So I have h, and then inside of the parentheses I end up with 2x plus h, since h squared divided by h is h, plus 1, since h divided by h is 1. And remember, all of that will go over h. So then my h's will divide away and cancel out. So I'll have the limit as h approaches 0 of the function 2x plus h plus 1. So if you remember, what we did was we went ahead and plugged in 0 when we were trying to find the limit. So we'll plug in 0 for h. When we plug in 0, we end up with, right here, 2x plus 1. So this guy right here will give us the value for the instantaneous rate of change once we actually plug in the value of x that we want. Because remember, at each different value of x, our rate of change is going to be different. So to find that instantaneous rate of change, we would have to actually plug in a specific point. So, for example, our instantaneous rate of change at 0, when we plug in 0, would be 1. So our difference quotient is 2x plus 1. All right, one last one. We are actually going to go through and find the derivative. So that's what our directions are going to be. Find the derivative. So remember, so when we're supposed to find the derivative or do any of those things that we had listed above that formula, you can use this formula to find it. Now, here in a little bit, finding the derivative, doing this is just going to get so cumbersome. So we're going to have a whole bunch of differentiation rules or derivative rules that we can use to be able to find the derivative in a lot quicker way. So here, let's try this function. Our function is going to be h of x, and it's going to be equal to 3x squared plus 2. So we're going to use that difference quotient formula. The limit as h approaches 0 of, remember we have f of x plus h. So wherever I see an x, I'm going to put x plus h in there. So I have 3 times x plus h squared plus 2. And then we have minus f of x. So we have minus, and then I'm going to put parentheses around that entire function that I have, 3x squared plus 2. And then remember, all of that goes over h. So we'll start to do a little bit of simplifying. I'll have the limit as h approaches 0 of 3 times x squared plus 2xh plus h squared, like we did last time, plus 2. And then we can distribute out that negative to my function, so we'll have minus 3x squared minus 2, and then all of that will go over h. So then I'm going to go ahead and distribute on out my 3. 3x squared plus 6xh plus 3h squared plus 2 minus 3x squared minus 2 all over h. So at this point, things start to divide away, or add away, I'm sorry. So right now I have the limit as h approaches 0. My 3x squared cancels out. I still have my 6xh. I still have my 3h squared. My 2 cancels out. And then I'm still over h. So if we take a look here, I still have an h in both my terms in the numerator. So I can factor that out. And inside the parentheses, I'm left with 6x plus 3h over h. My h divides away. So now I'm looking for the limit as h approaches 0 of 6x plus 3h. So remember what we learned. To find the limit, we can always go ahead and just go ahead and I can just go ahead and plug 0 in for h. So I have 6x plus 3 times 0. Well, 3 times 0 is 0. 6x plus 0 is just 6x. So that will be my derivative. Now, showing that that's my derivative, I can write in 2 different ways. So I could write h prime of x. That's said h prime of x. Or I can have dy dx equals 6x. So these 2 notations, they mean the exact same thing. But this is Lagrange notation. And this is Leibniz notation. So there's a whole thing about who invented calculus. Because it was invented around about the same time by 2 different people. So we'll have a little bit of a look into that on our block day. So I will see you tomorrow. Have a lovely day.